Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the generated essay, James Clerk Maxwell's 1867 treatise on the dynamical theory of gases, stands as a cornerstone in the development of statistical mechanics and our comprehension of matter's behavior at a microscopic level. This essay will undertake a detailed evaluation of the assertions presented within this seminal work, employing a structured, sequential analysis of its principal sections. It will probe the underlying assumptions, methodological rigor, and logical consistency underpinning Maxwell's groundbreaking investigation. We will assess the validity of his claims, taking into account the scientific context of the era and the subsequent evolution of the field. This process attempts to provide a holistic appreciation for the enduring impact and inherent limitations of Maxwell's contribution. Section 1, Introduction and Fundamental Assumptions. The initial portion of On the Dynamical Theory of Gases lays the groundwork for Maxwell's theory by establishing core assumptions regarding the nature of gases and the behavior of their constituent molecules. He postulates that gases consist of a vast number of particles in rapid, random motion. These particles are envisioned as perfectly elastic spheres possessing identical mass. Furthermore, intermolecular forces are considered negligible, except during instances of collision. Maxwell acknowledges the idealized nature of these assumptions, yet defends them as a necessary simplification for constructing a tractable theoretical framework. Critical scrutiny reveals a reliance on Newtonian mechanics, which, while appropriate for the scales considered at the time, would eventually require refinement as quantum mechanics emerged. A modern perspective might question the neglect of intermolecular forces, particularly in light of phenomena such as condensation and deviations from ideal gas behavior observed under certain conditions. However, these initial simplifications were essential to render the complex dynamics of gases amenable to mathematical analysis. Section 2, Derivation of the Velocity Distribution Law. A central feature of Maxwell's work lies in his derivation of the velocity distribution law, which describes the probability of finding gas molecules with velocities within a given range. His approach, involving considerations of symmetry and statistical independence, leads to the now-celebrated Maxwell-Boltzmann distribution. Maxwell's original derivation employs a heuristic argument involving orthogonal velocity components and assumes their statistical independence. While ingenious, this argument lacks complete mathematical rigor. Subsequent derivations, employing methods from statistical mechanics incorporating the concept of ensemble averages, have provided a more robust foundation for the distribution law. Moreover, Maxwell's original derivation does not explicitly account for the equipartition theorem, even though it is intimately related to his results. The velocity distribution law predicts that the average kinetic energy of gas molecules is directly proportional to the absolute temperature, a result which has profound implications for understanding thermal phenomena. Section 3, On the mean free path and collision frequency. Maxwell delves into the concept of the mean free path, defined as the average distance a molecule travels between successive collisions. He provides an expression for this quantity based on the molecular density and the effective collision cross-section. He estimates the collision frequency, that is, the number of collisions experienced by a single molecule per unit time. His analysis assumes that molecules travel in straight lines between collisions, a reasonable approximation given the dominance of kinetic energy over intermolecular potential energy at typical temperatures. The calculated values for the mean free path and collision frequency offer crucial insights into the transport properties of gases, such as viscosity and thermal conductivity. A careful validation of Maxwell's equation concerning the average mean path requires consideration of the distribution of molecular velocities. Not all molecules travel at the same speed. Slower ones experience a larger collision rate than their faster counterparts. Section 4. Viscosity and internal friction of gases. Maxwell applies his theoretical framework to explain the viscosity, also known as internal friction, of gases. He proposes that viscosity arises from the transport of momentum between layers of gas moving at different velocities. His kinetic theory predicts that the viscosity of a gas should be independent of its density, a surprising result that was initially met with skepticism. Experimental verification of this prediction provided strong support for Maxwell's theory. However, his original derivation omits consideration of the dependence of viscosity on temperature. Subsequent refinements, incorporating a more realistic model of intermolecular forces, have shown that viscosity increases with temperature, a prediction that aligns with experimental observations. Maxwell's approach, though initially limited, established the fundamental connection between the microscopic behavior of gas molecules and the macroscopic property of viscosity. Section 5. Thermal conductivity of gases. Analogous to his treatment of viscosity, Maxwell extends his theory to address the thermal conductivity of gases. He argues that thermal conductivity stems from the transport of kinetic energy between regions of differing temperatures. His kinetic theory predicts that the thermal conductivity of a gas, like its viscosity, should be independent of density under certain conditions. This prediction, similar to the viscosity result, initially challenged conventional wisdom. Experimental investigations confirmed this predicted independence, further bolstering Maxwell's assumptions. However, his initial calculation of thermal conductivity proves to be less accurate than that of viscosity. The discrepancy arises because the heat capacity of gas molecules, which determines the amount of energy transported, varies based on molecular structure. Maxwell's simple model, which treats molecules as structureless spheres, fails to capture this complexity. Section 6. Diffusion of gases. Maxwell examines the phenomenon of diffusion, which involves the intermingling of different gases due to their random molecular motion. He develops a theoretical expression for the diffusion coefficient, a measure of the rate at which gases mix. His analysis highlights the role of the mean free path and the average molecular velocity in determining the diffusion rate. He posits that lighter gases diffuse more rapidly than heavier ones, a prediction consistent with experimental observation. His initial treatment, however, assumes that all molecules have the same size, a simplification that is unrealistic. Subsequently, he recognized that molecular size affects the diffusion coefficient and adjusts for this in later work. The theory of diffusion highlights the intimate connection between microscopic molecular motion and macroscopic transport phenomena. Section 7 on the distribution of energy among molecules. Maxwell turns to the distribution of energy among different degrees of freedom within a molecule. This discussion anticipates the equipartition theorem, which states that each quadratic degree of freedom in a molecule possesses, on average, an equal amount of energy, specifically 1/2 multiplied by Boltzmann's constant multiplied by the temperature. While Maxwell doesn't explicitly formulate the theorem in its modern form, his exposition points towards its underlying principles. He recognizes that the internal structure of molecules, specifically their rotational and vibrational modes, contributes to their total energy. He grapples with the observed specific heats of polyatomic gases, which deviate from the values predicted by the equipartition theorem when considering all possible degrees of freedom. This discrepancy, known as the equipartition paradox, posed a significant challenge to classical statistical mechanics. The resolution of this paradox would ultimately require the introduction of quantum mechanics, which restricts the accessibility of certain energy levels at low temperatures. Section 8. Influence of external forces and gravitational effects. Maxwell considers the influence of external forces, particularly gravity, on the distribution of gas molecules. He derives the barometric formula, which describes the decrease in atmospheric density with increasing altitude. This formula arises from the balance between gravitational forces pulling molecules downwards and the random thermal motion tending to disperse them. He notes that the distribution of different gases in the atmosphere depends on their molecular weights, with heavier gases being concentrated closer to the ground. His analysis, however, neglects the effects of atmospheric mixing due to winds and convection currents, which tend to homogenize the composition of the atmosphere. Despite these limitations, his treatment provides a valuable insight into the interplay between gravity and thermal energy in determining the distribution of gases. Section 9, Imperfect gases and deviations from ideal behavior. Maxwell acknowledges the limitations of his ideal gas model and explores the behavior of imperfect, or real, gases. He recognizes that intermolecular forces, which are neglected in the ideal gas model, can significantly affect the properties of gases, especially at high densities or low temperatures. He discusses the van der Waals equation of state, which incorporates attractive and repulsive forces between molecules. This equation provides a more accurate description of the observed pressure-volume relationship for real gases than the ideal gas law. Furthermore, he considers the phenomenon of phase transitions, such as condensation, which cannot be explained by the ideal gas model. Maxwell's insights into the behavior of imperfect gases laid the foundation for the development of more sophisticated theories of fluid behavior. Section 10, Molecular collisions and chemical reactions. Maxwell investigates the role of molecular collisions in driving chemical reactions. He proposes that chemical reactions occur when molecules collide with sufficient energy to overcome an activation energy barrier. He explores the relationship between temperature and reaction rate, noting that reactions typically proceed faster at higher temperatures. His analysis foreshadows the development of transition state theory, which provides a more quantitative description of reaction rates based on the properties of the activated complex. However, his initial treatment neglects the complexity of molecular structure and the role of catalysts in influencing reaction rates. Maxwell's work initiated the application of kinetic theory to the understanding of chemical kinetics. Section 11, Loschmidt's number and molecular dimensions. Maxwell discusses the estimation of molecular dimensions and Loschmidt's number, which represents the number of molecules per unit volume under standard conditions. He draws upon experimental data for gas viscosity and diffusion to arrive at estimates for these quantities. He recognizes the inherent uncertainties in these estimations due to the simplified assumptions underlying the kinetic theory. Nevertheless, the values he obtains are remarkably close to the modern accepted values. Obtaining a reasonable estimate for molecular size and number provided powerful evidence for the reality of atoms, a concept that was still debated at the time. Section 12, Maxwell's demon and the limits of the second law. Near the end of the work, Maxwell introduces the concept of Maxwell's demon, a hypothetical being capable of sorting gas molecules based on their velocities. This demon, by selectively allowing faster molecules to pass into one container and slower molecules into another, could create a temperature difference between the two containers without performing any work. Maxwell used this thought experiment to question the absolute validity of the second law of thermodynamics. The second law states that entropy, a measure of disorder, always increases in an isolated system. Maxwell's demon, however, seemed to violate this law by decreasing entropy, while the demon cannot actually violate the second law because it requires energy expenditure to operate. This paradox has stimulated extensive research into the foundations of thermodynamics and information theory, leading to a deeper understanding of entropy and its connection to information processing. Section 13, Later revisions and experimental verification. It is beneficial to briefly acknowledge that on the dynamical theory of gases was not a static document. Maxwell revised and expanded upon his work over time, incorporating new experimental findings and theoretical developments. He refined his expression for the velocity distribution law and improved his treatment of viscosity and thermal conductivity. Furthermore, Experimental verification of his theoretical predictions provided strong support for his kinetic theory. The fact that Maxwell's work was subject to revisions speaks to his commitment to continuous improvement and the dynamic nature of scientific inquiry. Section 14. Conclusion. Enduring legacy of Maxwell's ideas. In conclusion, On the Dynamical Theory of Gases represents a pivotal contribution to the development of statistical mechanics and our understanding of the behavior of gases. Maxwell's ingenious use of mathematical reasoning, combined with insightful physical intuition, led to a number of profound discoveries. He derived the velocity distribution law, which describes the statistical distribution of molecular velocities. He connected the microscopic properties of gas molecules to the macroscopic properties of viscosity, thermal conductivity, and diffusion. Although some of Maxwell's initial assumptions and derivations were later refined or superseded by more sophisticated theories, his work laid the foundation for the modern kinetic theory of gases. His exploration concerning the equipartition of energy and the theoretical daemon provided invaluable insights into statistical mechanics, thermodynamics, and the role of entropy. It continues to generate discussion and exploration, emphasizing the lasting impact and fundamental significance of Maxwell's intellectual creation.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.